So that was equilibrium. We now look at one more type of a definition, which is steady state. What we mean by steady state is that in the system, so say whatever is the system, and it could be an open system or closed system, doesn't matter. We have the system boundary. Then if at any point, means any physical location, at any point in the system, there is no change of any property with time, any property, then the system is in steady state. Okay, so what we are saying is that if I have a rod and I'm heating it at this end and allowing it to cool at the other end, and let this system be operating for a very long time, then what we know is that the temperature at the core here is high and it keeps decreasing as we go out. So the temperature is a function of space, and so this rod is taken as the system. This rod is not in equilibrium. But if I stand here and I keep measuring this temperature now and after 5 minutes and after 10 minutes and like that, and if at any instant of time T1, T2 like that, the temperature is still the same, say whatever it was T2, 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 at any instant of time, then the system is in steady state. This simple definition has very far-reaching implications. The most obvious thing, we talked yesterday a lot about solar. Solar energy falling on any collector, photovoltaics or any type of a thing, is always changing with time. And from sunrise to sunset, it undergoes a value. After that, it becomes zero. That is the biggest problem with solar energy. It is not steady. In a nuclear reactor, we can manage it so that the heat generation in the nuclear reactor is steady with time, and then you can get continuously a constant generation from the system. So that's an example. But this has got a lot more things to do with it. When we will talk later on and we talk about efficiency or performance testing, all these analysis, whether it is for standardization or certification or problem solving, these concepts make sense if and only if the system is in steady state. And most real systems are not in steady. So for example, if you want to test a diesel engine and say what is the kilometers per liter, a car powered by diesel engine or say a bus, and say what is the kilometers per liter that I get, then the right thing to do would be to say, well, look, which gear will I drive, what speed will I drive, all of that is specified, what is the condition of the road, what is the ambient air temperature and pressure, which fuel we are using, what is the health of the engine. All these things have to be first well controlled, and then we operate it at a constant load for a certain period of time and then say this is the fuel economy of this, or how much ppm of NOx does it throw out, or how much hydrocarbon does it throw out, or how much particulate matter does it throw out. That's what one would do with a diesel engine. Look at the real life. Anybody who has been in traffic, cities like what we heard, all the mess that we saw in Gurgaon or in Bengaluru, recently in Delhi, the rains, even if those were not there, in normal times, do we have steady state? driving in a car? We make a measurement and we find that steady state operation is restricted to less than 10% of the time that a vehicle moves on a road. In many cases, even less. On the highway, it is going to be more. It is slightly more than this, but not very large. If the highway is clear, no other traffic, road is flat, everything is nice and clean, no winds, then okay. So in city conditions, you never have steady state. So to say what is kilometers per liter of a car is basically admitting that, look, I can't be bothered whether it was steady state or not. How much did I get? That's the only thing I will talk about. And that's fine. Then if you look at any of the power plants, whether it was nuclear or coal or anyone, the plant is operating over 24 hours, 7 days a week, and typically it will run at least 350 days a year without stopping, maybe even more these days. But what happens? During the daytime, the demand for electricity is more. At night, almost all activity goes down, the demand is less, and the electrical grid system is such that the generation has to always match consumption. So generation has to be exactly equal to consumption, which we call demand. And when that happens, this power plant will never ever operate in steady state. Another thing that will change the operation is that when you are burning, say, coal or oil with air, the coal has to be in steady state. All its properties must be same over 24 hours or more. And air also, all the properties must be same. But as you know, air undergoes a maximum temperature and a minimum temperature and some humidity also. So dry bulb temperature goes up and down, the relative humidity goes up and down. So the air going into the boiler is also not in steady state. The demand is not in steady state. So if I have to do an efficiency test or emission test on a power plant, it is extremely difficult. And so we have codes and standards which will give you the best possible way to measure it. But if a system can be well controlled, for example, if you are doing the efficiency test of an air conditioner, then there's a well-designed setup where you have the AC, is a window AC sitting there, one chamber here which is the hot side, one chamber here where you cool it. We maintain the temperature of these two constant and make sure that the system is in steady state for at least 4 hours, and then we take the reading, and this is completely isolated from the surroundings. Then you have a very, very reliable way of measuring its performance, and then the efficiency makes sense. In reality, this may not be happening. So steady state is a very important phenomenon, but since many of these systems do not follow in steady state, we can say, well, is the time dependence of the property very small? And how small? That's our discretion. And if you say it is small, then you say, okay, it is not in steady state, but quasi-steady state. And having made this assumption of quasi-steady state, then we can convince ourselves, okay, nice, now I got quasi-steady state, I can start talking about what are the properties and what is the process that is. So this is an assumption that we make in many cases, in some cases justified, some cases not justified. Okay. There are a couple of more questions. Okay, so we have still got the reversible question is there. We'll take that up. But before that, please elaborate on chemical equilibrium. Okay. What we are saying is that what is chemical equilibrium? What we are saying is that if the concentration of different species at every place is the same, then the system is in chemical equilibrium, which means that we say that there is some chemical which was there, I will just call it chemical X, and in air we have N and we have O. If at every point in the room all these three concentrations are the same everywhere at every point at any instant, then the system is in chemical equilibrium. Else it is not in chemical equilibrium. Okay, so take for example that example, the mosquito repellent thing. Very close to the wick of that thing, the concentration of that repellent is high. As you go out, the repellent concentration keeps on decreasing. And this is what happens in the room. So here the concentration of X, which is the repellent, is more. Here the concentration of X is less, and far away it is even less. So in the same room, if this was different, then the system is not in chemical equilibrium. If it is same, then the system is in chemical equilibrium. Okay, so we now go back to our process and look at the next most important definition. And this is the definition of a reversible process. So firstly, we are looking at a reversible process. That means there is a change of state. Going from state 1, the system went to state 2. During this time, both the system and the surroundings had some work. The system had Q, the surroundings had minus Q. System had minus W, surroundings had plus W. Okay, so whatever was the heat on the system, the opposite happens on the surroundings. So that means that in every process, there is something happening to the system and something happening in the surroundings. Okay, and we said that a process is reversible if at any instant we can reverse this process, that means get back from state 2 to state 1, but in the process there is no permanent change on either the system or on the surroundings. Okay, this is an important thing, no permanent change on system or surroundings. That means both the system becomes what it was before the change and the surroundings also become the same before the change. Then that is permanent change, which not an instantaneous one-shot deal, but something that is always going to be there. So let's take a simple example. Here is say a block of material which is at temperature T1 sitting in surroundings where T2, where T1 is less than T2. So the body is cold. Okay, or let's say the other one. T1 is greater than T2. Easy to understand. So the first thing to do is to see well what is the system and what is the process. The system, we say, is this thing, and there is no work transfer taking place, no mass transfer taking place in this. The only thing that happened was for the system there was Q out, and for the surroundings, which is now excluding this, everything else in the surrounding, there is Q coming in. So this is minus Q, this is so this is entering the system, surroundings. And say this was air, this air got hot. And then we reached a state where say we started off with 70 degrees C T1 and T2 was say 20 degrees C. After some time this became say 50 degrees C and this became say 35 degrees. I'm just putting some numbers, doesn't matter. So the process was here. This was the initial state, this was the final state, and this was our process. And now we say, is this reversible? And then you say, well, how can I didn't expend any work, we did not burn anything, nothing has happened, this thing went by itself from here to there. Is it possible for this energy to go back this way and you have heat there, so that this comes back to 20 and this goes back to 70? So we are saying, can it by itself, this 50 becomes 70 and this 35 becomes 20? And you all know from experience that you cannot have heat transfer by itself going from a low temperature to a high temperature. You say, what is the next best thing I can do? Well, you said, no, if I want to bring system back to its original state, I need to have something in the surroundings which is higher temperature, and say, okay, around this I will burn some fuel and produce gases which were, I want to get it back to 70 degrees Celsius. So I produce a temperature of at least say about 80 degrees Celsius or 90 or 100 degrees Celsius. This will cause heat transfer back and T1 will come back to 70. So what will happen? The system got restored to its original state. It got reversed. But what happened on the surroundings? We got some permanent effect there in the form of, say, burning of a fuel, or putting an electric heater which consumed electricity, or we put a heat pump, say like a refrigerator type of a thing, where this took electricity and took energy from a low temperature which was 20 degrees Celsius and sent it out. All of these brought the system back to its initial state, but the surroundings underwent what we call a permanent change. We expended electricity to drive the heat pump, or we expended electricity to heat it up, or we burnt a fuel to heat it up. That got depleted permanently in the surroundings, and so that classified as a permanent change. And so you could reverse the process with permanent change in the surroundings, and so this is not reversible or irreversible. That is one way that things happen, that heat transfer through a finite temperature difference is always irreversible. And you can argue yourself that I want to make a cup of tea, I got so much water which I want to heat to 95 degrees Celsius, it is 25 degrees Celsius. I have option number one, I can heat it on my stove where the temperature of the gases that are flowing around it like this, and the flame itself is a 700 degrees Celsius, and the gases going here are say 200 degrees Celsius. Somebody says, well, it will take some time, I want it a little more quickly. The fellow says, okay, why don't you put up an oxyacetylene flame over there? This is 2500 degrees Celsius, just put it below, you will heat it up very quickly. Somebody says, no, that's not good enough. I'll just take a heater and maintain a temperature of, say, 100 degrees Celsius on this. And the third person says, look, when it is 25, I'll put a heater of 25.1 degrees Celsius. When the water becomes 25.1, I will take this temperature to 25.2 degrees Celsius, and like that, finally, I will get 95.1 degrees Celsius and the water will become 90 degrees Celsius. Okay, so I'll leave this question for you to think out. What is the thermodynamic implication of these things in terms of what we talked as irreversible heat transfer? We know that these are irreversible. What can we quantify as the gain or the loss because of irreversibility? Okay, so this we will leave off, and you can argue then that if the temperature difference between the heat transfer happens across a delta T, which is infinitesimally small, and we are not saying what this means, then theoretically only we can argue this could become a reversible process. I am mentioning this because this is hugely counterintuitive. We know that heat transfer just cannot be reversed without any permanent change in the surroundings, but here is a concept, and it's purely a concept that we develop, that if by some means this temperature difference is exceptionally small, then with an exceptionally small amount of change in the surroundings, we can reverse that process. That's an approximation which will come out later on as a very important approximation for us. So if you think about it, it's not very easy to appreciate this, but the concept of reversible heat transfer in some way sounds counterintuitive, but it's a useful concept. In reality, it's practically impossible to do. What are the other things that cause irreversibility? Friction. And this is not only friction of, say, a block set sliding on a table, but also we take, say, water, stir it, and leave it. The water had energy because it's in motion, kinetic energy. Gradually, it stops, and everywhere it becomes zero. So, what happened? The thing was that all of that got dissipated because there was friction between the elements of the water itself. So, friction is between solid, 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 liquid, 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 and when I put a liquid, I also can include a gas in it or a fluid in it. So there is friction everywhere, including the air. Okay, so that friction causes this because when friction happens, work is dissipated and it's converted into heat, and you just cannot get the opposite thing done. Then there is unrestrained expansion. So we said unrestrained expansion is irreversible. So let's talk about what becomes restrained expansion. So that's a piston sitting there, and there's a pressure here. This is producing a certain force, and this is a force which is just about matching this force. So this thing is pushing against this force, and the piston moves a small distance and comes over there. The pressure inside goes down, and then it pushes that force and goes back. So there's a very, very small steps in which the force that is acting on the piston is practically the same as the force that the fluid is exerting on it. So this force, which is the restraining force, is very much equal to the force that is exerted by the system on the piston. And if the two are pretty much the same, whether it is expansion or compression, then this becomes an example of restrained expansion or compression. And this we say is reversible. Okay, so this is reversible work. What is unrestrained expansion? Well, you're holding it down with certain force at this point of time, and then suddenly we just let it go. So we know that you let the bicycle pump compressor and let it go, it just goes up and down, pops a few times, so it will go up and down, and finally it will settle down somewhere there, which would have been its equilibrium position anyway. But during this process, the only work it did was to move the piston. If the piston had no mass, it didn't do any work. The surroundings, there was no work on the surroundings, work was zero. But if you want to get it back from here to there, we would have to do work on it to get it back to the initial state. There we would have to expand work, and so while unrestrained expansion, we got no work. To restore the system back to its initial state, we have to do work. And that's what makes unrestrained expansion irreversible. So this was friction was also causing irreversibility. Another example of unrestrained expansion is that we take a chamber in which this side there is a gas and this side there is vacuum. And we rupture these, this gas expands. It doesn't do any work, but to put it back, we need to do work to get back to the same thing, and that work is permanent change on the surroundings. Then there is mixing. Mixing means mixing of two different species. If we say that I am going to put, say, any gas into the air, the two will mix, and say now I want to separate the two out, but naturally they won't happen. We would need to put in some work, maybe some heat, and these will be permanent effects on the surroundings, and then only you can restore the system back to its original state. Okay, so these are some of the things that cause irreversibilities. Okay, there are questions, so we have few minutes left. I take some questions and the rest I will then respond to it on the web.
Good morning, sir. My name
Yeah,
is Manjeet Singh. I'm a fourth year mechanical student at Dronacharya College of Engineering. And my question is, sir, can we use biogas as a fuel in internal combustion engine made from cow dung? And what will be its efficiency and how much distance the vehicle will cover in 1 kg of gas?
okay, so the question is, can biogas be used as a fuel in IC engines? Well, biogas is strictly methane 50% plus CO2 50%. And of course, so either this way or you can remove the CO2 and get the methane and use it. In any way it is done, it has been done, and it's fairly standard technology, it's already available commercially. So there is nothing new to be done on that. Gas engines are available from most manufacturers. As far as the mileage and emissions go, you can read up on the literature on the web. I won't go into the details of it. I won't go into the details, the data is there. Yeah.
We have already studied that heat and work depend on the path. Why is it so?
Okay. Say that again. Heat and say that again. Heat and
Heat and work depend on the path. They are path functions.
okay. Okay. So the question is, I mentioned that heat and work will be associated with a change of state. So we have gone from state 1 to state 2, and I also mentioned that when this change of state takes place, depending on the path that one follows, it will decide that Q and W in each case is going to be different. The question is, why is this so? Okay, so I'll give an example and then you'll see that. Suppose I have a gas which has to expand from here, and this much is the volume change, and in the initial state 1 there is certain pressure and say certain temperature T1, and then it reaches this state, and here you have T2 and T2. To get from here to here, one could do is expand this, and then if the temperature doesn't match with the T2 that you have, you can either add heat or you can cool it. Or alternately, you can first heat it and then allow it to expand so that it becomes fluid. So you can, at least two things are possible, that you first do some work and then give plus some heat, or first heat it and do some work, or any combinations of these. Some work that brings it up to here, then you heat it, then some work, then some more heat, and it brings it up to here. So what is happening in each one of these cases is that the final state is the same, whatever we had asked for, but in each one of these, when we do the calculation, the Q and W for the process, Q12 and W12, these will be different. The exact numbers that will fall on this, we will come to that when we look at the laws and finally the properties. When we look at it, then you do a numerical and you will see that Q12 at path A, where you first heated it and then expanded, or second, when you expanded it and then heated it, those heat and the work with those processes will be different. Okay, so now, I'll leave this example here, but we'll come back to it again and again in the next two modules and also in the final module when we solve problems. We'll come back to this many times.
Hello, good afternoon, sir. My question is, every reversible process is a quasi-static process, but every quasi-static process is not reversible process. Why is it so, sir?
Okay. Okay, this is that we are talking of a process, and we are saying, I will not use the word quasi-static, I have said the quasi-steady process. In the quasi-steady process, what we are saying is, at any instant of time, we are assuming that the system is in equilibrium. In between the times, the system may not be in equilibrium. The second thing is, in reality, the system may not be in equilibrium, and this could be in quasi-equilibrium. So the difference is there, that equilibrium is defined only for a state, whereas a process being quasi-steady is for a process which is a change of state. So two are very, very different things. They are not the same. Okay, one last question, then the remaining I'll put up on the web. Yeah.
Sir, what is the advantage of reversible process?
Okay. So the question is, what is advantage of reversible process? Okay, it's a good question. Purely from a definition, the reversible process is something which we will see later on as being the most, what we call, efficient process possible. And what it does is, if you can get reversible, so you have reversible work or reversible heat transfer, the less the quantity amount of irreversibility, the more is what you can gain as output. Okay, I'll go back to the schematic of that nuclear reactor, that system that I have done. Here, when we cool water and bring it down to say 45 degrees Celsius, then we heat it in a boiler or a nuclear reactor and bring it to say 350 degrees Celsius. That means we are using a high temperature source to heat water from 45 to 350. But if somehow we can heat the water here by using some of this steam, or not this steam, some of the steam from here, and raise its temperature to say 100 degrees Celsius, then the heat transfer in the boiler or in the reactor will now occur over a smaller temperature difference. What that did, it reduced the irreversibility in the heat transfer process, and because of that, the efficiency of this cycle went up. And that's what we try to do in many of these devices, is that if there is heat transfer taking place, we try to reduce the temperature as much as possible. That way, the system may get more complicated, the system may get bigger, but that becomes the most efficient thermodynamic system. Later on, when we look at cycles, we'll find that the reversible cycle is the most efficient cycle, say from converting heat to work. And we will see that to get it reversible, everything has to be very slow, differences have to be very small, friction doesn't have to be there, which will always be there. It's extremely slow and very, very difficult to make and practically impossible. In reality, you want everything fast and quick. But this gives us a benchmark of what is the sort of the maximum possible efficiency, if I want to call it efficiency, or the work or the heat that I can get from a process. So that's why reversible process is a concept which tells us what the best possible thing you can achieve, and in reality we do everything to get to that process. So that's the only advantage that we have in this concept. We'll come back to this again when in all the modules that we do subsequently.